Or is it a, remember that? Like for example, for certain gates, for example an AND gate, if any input into the AND gate is a 0, the output will always be fixed to a 0. Yeah? And for OR gate, if one of the inputs is a 1, if any of the inputs is a 1, the output will always be a 1. What did we call that? What did we call that? Is that called what? Null element. Identity. Yeah? The identity. So the identity for the NAND gate is a 0. Right? The moment you place in, yeah, the moment you place in, what do you call, sorry, not the identity, the null element. The null element, no, the identity. The moment you place in a 0, right, the output will always be fixed to a 1. So that's important. Now let's look at the latch. Now the latch, obviously in our latch, it's configured like this. There's 2 inputs and 2 outputs. And according to our design, you have Q and Q bar. You have Q and Q bar. So we would like, as the designer, we would like one output to be the opposite of the other. These two have to be opposites of each other, right? Now the thing about our circuit is, this is the first time you will hear this, our design is partially functional. It's partially functional. That's the key point. That's where students get confused. The design is partially functional. It functions sometimes, and sometimes it doesn't give the right answer, right? So what we're going to do is we only utilize the particular circuit, right? We only make use of the circuit when it functions. So case 1, if we set S to 0 and R to 1, like out of the blue, if we now start processing R, we don't know what the other inputs are. Can you see? We have no idea what the second inputs are to each into the NAND gates, because we don't know the outputs, right? So the way to do it is to process it from one side and see if it stabilizes, if the circuit stabilizes. Stabilizes means it's now giving a consistent answer. So let's try the 0, 1. This is a repeat of Monday's lecture, right? And then we'll move into SR Latch, and then, sorry, this is the SR Latch. From here we'll move to the SR flip-flop. From the SR flip-flop we'll move into the SR flip-flops, the truth table for the SR flip-flop, the excitation table, the state diagram. There's so many other things happening, right? It's going to happen very quickly, right? So you have to have this, your basic, what I said, the DNA has to be strong. All right, now, this is 0, this is 1, right? In our truth table, usually we do 0, 0, 0, 1, 1, 0, 1, 1. But okay, I'm over here, I'm starting off with a particular, I'm taking you around the neighborhood, right, from different sides, so that you can visualize what is happening. Remember, what I said, the circuit is partially functional. Sometimes it is stable, sometimes it is unstable. It's not giving consistent answer, right? Okay. And remember, this is sequential logic. So sequential is different from combinational. So 0, 1. If we have a 0 here, right, we don't know what the input is. But hey, according to this thing here, for sure shot, at least we now know that Q will be 1. So Q is 1. We know sure shot. So if Q is 1, that 1 gets fed down over here. What was this guy? That was 1. Remember, initially we didn't know what was this. Yeah, but now we've got a figure because it's all instantaneous. These gates work at the light of speed of light. All right. So that is 1 because this was 0. So obviously, if any input is 0, doesn't matter what here. There would be some noise here. That becomes 1. Once that becomes 1, this 1 comes down. 1 and 1. 1 and 1 gives you a 0. So now, according to our design, they've got to be opposites of each other. So if Q is 1, Q bar is a 0. So hey, that's happy. We are happy that it's giving us a consistent answer, right? And if this is 1, what was this? This was a 1, this was a 0. Let's go trace it back the other way. So this came out to be a 1 according to this guy. I should have a stick here. Eh? Any stick around over here? No? Okay. Right. If this is a 1, this is giving a 0. We just worked it out. Let's now trace it back. This 0 goes back here. This 0 goes back there. Right? Okay, the moment that is a 0, hey, the moment that is a 0, obviously for NAND gate number 1, look, I've labeled that, NAND gate number 1, the moment that is a 0, 0 NAND 0 will give you a 1. That flows back downwards here, 1. 1 NAND 1 for NAND gate number 2 will give you a 1 NAND 1 will give you a 0. So now can you see it's going in cycle, but the answer is consistent. The answer is stable. It's not changing. It's not changing. All right. Now, immediately after this, we apply the 1 1. We apply 1 1. We change the input and we say, okay, 1 1. Right. Now, the thing about this is, and I've introduced this on Monday, 1 1 is only a follow-up command. It cannot be done initially. The only initial commands can be 0 1 or 1 0. Right. Okay. Now, what have we done in 0 1? By doing, okay, the letter S stands for set, the letter R stands for reset. Okay, set reset. That's the full name of it. Okay. Now, by setting S to 0, right, what we've done is by making S 0 and R 1, we have set Q to 1. Right, setting means to fix or to place a 1 in Q. Right, if Q is equal to 1, then Q bar should, the word should, I'm using the word should, equal to 0. It should be the opposite. Now, immediately after that, I'm doing 1 1. Now, 1 1, right? I'm placing 1 1. Remember, 1 1 is a follow-up command. Can never be, can note this down. I'm saying a lot of things now verbally. I'm not writing it down, but you can pick up. If you did not grasp it in our Monday's lecture, you can note it down on your exercise book, all right? 1 1 is a follow-up command, not an initial command, right? Because if you do an initial command, let me elaborate on that. Hey, let's forget about everything. Let's do a clean, fresh circuit. We do a 1 1. Yeah, come here, let me see. Right? We do a 1 1. What's the problem with the 1 1 as an initial command? We've got a 1 here and a 1 here. Initial, fresh command, 1 1. We don't know for, if SNR is 1 1, we don't know what is the second input into the NAND gate for NAND gate 1 and NAND gate 2. What is the second input? See, those two are 2 input NAND gates. We don't know. That could be noise. And it could be anything. Right? And our answer is variable. It could change. So there's no sure short answer. So that's why this is a partially working circuit. And we've got to use it in a particular way. Right? Okay? It's a partially working circuit. All right? Okay, and we've got to use it in a particular way to our advantage. To our advantage. So it's like a very fussy circuit, not partially working. It's very fussy, right? It's like it's very fussy, and you've got to approach it in the right way. Press the right buttons, and then it will give you what you want, like your girlfriend, right? Very fussy. You've got to approach in the right way, right? Say the right things, and then you get what you want. Okay, all right? Okay. Okay, so the input has got to be correct. Okay, now, 1 1 is a follow-up command. 1 1 is a follow-up command. Now, if 1 1, you place 1 1, right? Okay, and it's follow-up. It's depending on what was there before. Now, what was in Q before? Q was already a 1, and Q bar was a 0. So Q bar was a 0. So S is 1. Q bar is a 0, Q will become 1, right? Q will become 1, it travels down this way, right? Now, NAND gate number 2, 1 and 1, 1 NAND 1 will give you a 0. So, again, you can trace this back upwards, 0 goes back up over here to NAND gate number 1, S was a 1, 1 NAND 1 gives you a, 1 NAND 1 gives you a 0. So, can you see the circuit is now stable? It's giving the same answer, right? And it so happens, we notice something, we observe, hey, when we place the 1 1 here, the output is the same as previous, same output. Let's try another combination now. Let's now do a 1 0. Let's now have S equal 1, and we're going to case 2 now, right? S equal 1 and R equals 0. S equal 1 and R equal 0. Now, in that particular case, according to this, right, instantaneously, because there's a 0 on R, instantaneously, no matter what you had before, right, that's the thing about these two, 0, 1 and 1, 0, right, S is equal to 0, I mean, SR is 0, 1 and SR is 1, 0, right, because R is equal to 0, instantaneously, because of this rule that 0 NAND X will always equal to 1, right, this Q bar will become 1. We're looking at case 2, line 1, the upper line of case 2, right? Okay, Q bar becomes 1. This one travels up to NAND, travels as a feedback to NAND gate number 1, right? So, if it travels as a feedback to NAND gate number 1, S is 1. 1 and 1 NAND 1 gives you Q of 1 NAND 1 gives you 0. We're looking at this line here. So, we now have Q equals 0 and Q bar equals 1. Hey, no worries, right? It's giving according to the design, they're supposed to be opposite of each other. Now, we now apply a 1, 1 after this. Now, even after that, you say, hey, how about immediately after 1, 0, I apply a 0, 1. If you do that, same thing. It'll flip back. So, the two situations, if you look at the truth table, there's two inputs, right? Two input, therefore, our truth table will consider 4 possible combinations. The thing about 0, 1 and 1, 0, 0, 1 and 1, 0 is that it will always give a consistent answer. It doesn't matter whether you do it as a follow-up or whether as you initiate, right? Whether follow-up or initiate, it gives you a consistent answer. Just note that down, eh? Consistent answer. It will always give you, if you do 0, 1, it will always give you Q is 1, Q bar is 0, right? And if you do 1, 0, it will always give you Q is 0 and Q bar is 1. Always consistent answer. It's fixed answers, right? So everyone is happy with those two. Now only left is, if you look at your truth table, 0, 0, 0, 1, 1, 0, 1, 1. 2 items are left. 1, 1, we are still discussing 1, 1. Now let's look at 1, 1 now. With 1, 1, which is a follow-up to 1, 0, right? Look at case number 2. 1, 1 as a follow-up to 1, 0. Okay? Okay, now. 1, 0, when we applied it, and the thing about 0, 1 and 1, 0, SR is 0, 1 or SR is 1, 0, you can start it as an initiator or it can be a follow-up. But it will give the same answer. Now, let's look at 1, 1. 1, 1 can only be a follow-up. I hope you note these points down. Eh? 1, 1 can only be a follow-up. Now, 1, 1, oops, all right. Okay. We've just done a 1, 0, and we find that Q is 0, Q bar is 1. Now we do a follow-up as 1, 1, right? Now, when we do a follow-up as 1, 1, it is dependent upon the previous input, because there's no zeros in the 1, 1, right? Okay. Now when we do a 1, 1, we remember that Q was a 0. So 0 comes down here. R is 1. 1 and 0 gives you a 1. So Q bar becomes 1, and that 1 travels from Q bar, goes up to the second input of NAND gate number 1. So 1 NAND 1 will give you a Q of 0. So our answer is, and if we now follow that up again, if Q is 0, 0 comes down here from Q into the feedback into the NAND gate number 2. So 0 NAND R was 1, will give you 0, NAND 1 will give you 1. That 1 now travels back up into NAND gate number 1. So can you see the answer is now consistent, it's stable, right? Okay, so what do we learn? What is the observation here? 1, 1, we cannot kick it off. If you get a fresh circuit, you don't know what's happened before. Fresh circuit, first time it's being on, right? You supply a 1, 1, you don't know what our second inputs are. There's no way to predict what your second input into each of the NAND gates is. So that's why it's always going to be a follow-up. It could be some noise. And if the noise is 0, output will be 1. If the noise is 1, output will be 0. So it will become an unstable output. But 1, 1 as a follow-up. What do we notice in 1, 1 as a follow-up? it always gives the same answer as what was there before. So 1, 1 in case 1 gave the same answer as before. 1, 1 in case 2 gave the same answer as before. So 1, 1 is actually memory. It's remembering what was there before, the answer from before, right? In a normal case, like the 4 security camera case, right, 4 security sensors case, the moment the input changes, the output changes, right? Over here, the input changed, and it gave in one round, it usually, the same set of input should give the same set of output. But over here, it's giving a different output for case 1, different output for case 2. Yeah? So it's memory. It's saying what was there before. It's giving you what was stored in memory. Now let's try case 3. Case 3 is the one, remember my original statement was that, hey, this is a fussy circuit, and it only gives consistent answers sometimes. Now the first point was, if you apply SR as 0, 1, it will make Q as 1 and Q bar 0. And if you apply 1, 0, it will give Q as 0 and Q bar as 1. And if you apply 1, 1, you cannot apply it as an initiator. You can only apply it as a follow-up to 0, 1 or 1, 0, and it will give you the same answer as previously, right? It's memory. But it doesn't give you consistent answer. It just gives you the same answer as before, depending on what your input was before. Now case 3, so we've done 0, 1, 1, 0, 1, 1. We've done 3 of the truth table. You see there's 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. So we've done the bottom half, we haven't done 0, 0. So if we apply 0, 0, 0, 0, so moment one of the thing is 0, 0, 0, the moment one of the inputs into the NAND gates is a 0, you get a 1 here and a 1 there, right? Because both inputs are 0. Now this is the confusing part. So the 1 travels down this way, 1 from Q will travel down into the second input of NAND gate number 2. 0 NAND 1 will give you a 1, right? 1 will travel down over here to the second input of NAND gate number 1. 0 NAND 1 gives you a 1. So you do get a 1, 1 output. So stable output, but already we're getting some contradiction now. Our design, we wanted it. In our design, we wanted these two to be opposite. Even though this is giving a consistent answer of 1, 1, right? It's giving a stable answer of 1, 1, doesn't flip-flop, right? But what is happening is we've already broken one of the rules. It is not respecting, so you can just write down for the 1, 1, 0, 0 input, it is not respecting that Q and Q bar should be opposites. It's giving a consistent, Q is equal to Q bar, which we wanted it to be opposite. We wanted it to be opposite, right? So it is inconsistent now. It is not respecting our design, right? The design was only respected with 0, 1, 1, 0, and 1, 1. Now, as a follow-up, remember what we've learned so far is 1, 1 should be 1, 1 should be memory. It should give what your answer was from before. Let's apply a 1, 1 as a follow-up to 0, 0. If we apply a 1, 1 as a follow-up to 0, all right, what happens is that if we apply as a follow-up to 0, 0, so if we do a 1, 1 here, this Q and Q bar was already 1s, right? 2 1s as a follow-up. So 1 and 1 will be 0. Q and Q bar will both be 0. So we've got 2 problems now as a 1, 1 as a follow-up to 0, 0. 2 problems. What do we see? We see that, hey, firstly, we're getting both answers 0, 0, so it does not respect the Q should be opposite of Q bar, right? Does not respect that. Secondly, 1, 1, did it remember? No, it did not remember. That's another problem. It did not remember. So memory failure in case 3. 2 problems, not just 1, 2 problems. Memory failure. So therefore, what we say is, hey, we know it's a fuzzy circuit, right? We're not going to discuss it. It's like, so certain issues with your friend or girlfriend or whatever, you don't discuss because you know it's going to get a very volatile response. So we don't go to case 3. We don't feed case 3. Yeah? All right? So case 3 is, we say, invalid state, not used. Invalid state, comma, not used, never used, don't go there, all right? Okay, so now, eventually, we are able to summarize our thing like this. 0, 0, we just say don't use, not used, right? 0, 0, not used, because if you allow a 0, 0, because we know 0, 0 will give you a 1, 1 for sure, but if you allow that, that means your memory line will start to fail and all that. So you say don't use that, right? Don't use that. 0, 1, whether you initiate the circuit or a follow-up after a 1, 1 or whatever it is, even you can do 0, 1 and then 1, 0. It will always give you a consistent answer of 1, 0, right? And that's called set, right? That's setting Q to 1. Now, 1, 0 will always give you a 0, 1. That's also good. These two are, let's say, the sure short boys, right? They always give you, they always deliver on their promise, these two inputs, 0, 1 and 1, 0. They'll always say set or reset. They'll always give the same answer. Doesn't matter what the issue was before. All right, now, the situation with 1, 1. 1, 1 is a bit like follow the leader, right? It will always give the answer of what was before. And remember, we've already said never use this. So this line is pretty much cancelled. So 1, 1 will only give you whatever was the answer from before. The answer, not the input, the answer from before. It will give you memory. It will give you, it will recall the answer. It's like on your calculator, memory recall, right? Or RCL or something like that, right? You have, yeah, is that RCL on your calculator? Yeah, okay, right. Memory recall. So it's basically doing a recall. Another thing they use is, they say it's hold, right? It's holding the answer, right? Okay, now, let's now extend our circuit. Now that was revision, guys. That was revision. Let's now extend our circuit. We now extend our circuit as such. Okay. Now, you see this here in the dotted red line, that's our SR latch. That's the original latch, right? So the new inputs, because we use that S and an R over here, let's label, for the sake of it, the new S and the new R over here. You can label it S prime or whatever it is, right? But S prime also can make a mistake. S prime, sometimes some people use the prime to mean inverted, S bar. Yeah. So I use S star and R star. Okay, now let's look at it from this point onwards. Only up till here, right? Only up till there. The moment clock is 0, let's look at number 1. Let's look at number 1. Two. All right. The moment clock is 0, what can you tell me about S star? If clock is equal to 0, right, S star will always equal to, in terms of S, will always equal to 1, right? Doesn't matter what your S is. And what can you say about R star? Will always equal to 1. Doesn't matter what your R is, the moment the clock is 0. Now let's look at the other one. What if your clock was 1? What if clock is equal to 1? Right? What if clock is equal to 1? What can you tell me about S star? If clock is equal to 1, what can be S star? R has no influence on S star, right? And S has no influence on R star. So if this is a 1, we've discussed 0. With 0, S and R, S star and R star will always be fixed to 1, right? No issues about it. Now the moment this is a 1, right? So S NAND 1, 1 NAND S gives you what? Okay, let's write the formula. What is S star equal to? Write it out, guys. What is S star equal to? Let's write the formula out. What is the algebraic expression for S star? Maybe I'll put it down over here on the side. I'll just zoom out a little bit, guys. What can you tell me about S star? So if CLK is equal to 0, then what happens? Right, I'm just going to zoom out a little bit so that you can see my, there's not enough space over there. So S star is equal to 1, R star is equal to 1, right? If CLK is equal to 1, then S star is equal to 1 NAND S, which is what? And R star is equal to 1 NAND R. Yeah, you guys see this over here in the corner? Right? And what is that equal to? S bar. R bar. 1 NANDed with anything gives you the opposite. Yeah? If you remember the truth table, 1 NAND anything will be the opposite, will be the invert. Is that everyone happy with that? Okay, now, so basically, S star and R star are, if clock is equal to 0, they'll be fixed to 1, no options. If clock is equal to 1, they'll be the opposite. So that is some basic intuition. Now, let's now have a look at the truth table. We were doing this truth table, right? Let's look at the truth table. I'm going to zoom out slightly. All right, let's look at the truth table. And this, we spent a bit of lecture on repeating things from the previous lecture, but that's okay. This is very, very important. Okay, now, we have 3 inputs. If you look at the circuit, how many inputs? 3 inputs. If you look at the outputs, how many outputs? 2 outputs. 3 inputs are S, clock, and R. How many outputs? 2 outputs, Q and Q bar. I've just put this thing called S and S star only to help you, you know, just to help us to see the intermediate part, the intermediate phase. So if there's 3 inputs, guys, how many lines on our truth table? 8 lines, right? But instantaneously, we already know the intermediate part that, hey, if clock is 0, doesn't matter what these two are, S and S star will be, S star and R star will be 1, 1. Yeah? Okay, we already explained that. Okay, now, if clock is 1, now we've got some areas to play. S is 0, R is 0. What happens to S star and R star? If clock is 1, what did I say? If clock is 1, here in the corner, if clock is 1, S star and R star becomes flipped. It's opposite. So this one will become 1, 1. Yeah? Everyone getting with me now? Okay, that's 1, 1. Now, if 1, 1 is going in here, all right, if 1, 1 is going in there, okay, what is this circuit of? This part in the dotted box. That's just the SR latch. This circuit is, by the way, this whole circuit is the SR flip-flop. Okay, now that's a different circuit. There's different circuits, different names. Right? This is by adding this clock and all that. And why do we need the clock command? To have control, to enable it. Right? To have control over the circuit. To switch it on and switch it off. Remember when you did mux and decoder, encoder, you've been playing with enable line. So that's the thing here. Enable line just switches it on to memory. All right, now, 0, 0. So basically these two lines, if this is a 1, if clock is a 1, what does S star and R star become? They become the opposite, the inversion of S and R. So 0, 0 in SR will become S star, R star will become 1, 1. 0, 1 will become 1, 0. 1, 0 will become 0, 1. And 1, 1 will become 0, 0. Now S star and R star are actually an input into the, if you look at the dotted line, is an input into the SR latch. We've already done the SR latch. Right? So if the input into the SR latch is 1, 1, what do we say? It's memory. Right? It doesn't give you a definitive answer. It gives you an answer based on the previous input. Now 0, 1 becomes 1, 0. S and R, if it's 1, 0, 0, 1 will become S star, R star will be 1, 0, which gives you Q and Q bar of 0, 1, right? Which was what? Reset. Yeah? 1 0, that's again a sure shot thing, 0 1 and 0 1 0, that becomes flipped to become 0 1, that becomes set. Now 1 1, entry of 1 1, right, becomes flipped, is inverted and becomes 0 0, and we say, hey, we're not going to use that, so we don't even give an answer. We're not going to use that, even though there is an answer, but we say we're not going to use that. So we're only going to use this much, the first 4 lines of the truth table. In fact, it's the first 7 lines of the truth table. Why? Because line number 0, we just said, we just cancelled out 4 lines because we know it's not going to change. The answer will always be memory, 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 memory. All right? Okay, so that's our flip-flop truth table. That's our flip-flop truth table. All right, now, let's go one step further. Let's now reuse that information, and we reuse that information. Maybe I write it on the same piece of paper. So now we don't need to look at the circuit, we look at this particular thing here. Now, I want you to tell me about this. This truth table, if we look at it, Q is, when we talk about memory, when we look at memory is giving you the previous state. So now we have to now think along the lines of, you see, when we talk about memory over here, it's actually you are asking it for what happened before, previous state, or current state, next state. Yeah? Okay, so memory, let's say memory is the next state, right? And so there's Qn and there's Qn plus 1. Qn means current and Qn plus 1 means next. Or you can use some other designation. They say Q and Q star sometimes. Q and Q star. Or some textbooks use capital Q and lowercase q. What is it about memory? When we ask for memory, it's actually dependent on the previous state. Yeah? Right? Or if you look at it from now, the future state is dependent on the current state. Yeah, it's going one step back always. It's looking backwards. Memory, when you ask you, do you remember what happened in week 1? Do you remember what happened in week 7? We're always looking backwards. So from the future point, we are looking backwards. So let's now rewrite this table in terms of memory with respect to memory. Right? Okay, so let's now use this little space over here. All right, now, so again, we have clock as our input. That's always going to be an input. We have S. We have R. Okay. This is where it becomes very, very tricky. Right, and this is a double line over here. Now my inputs, okay, 0xx. You guys understand why I put 0xx? So this table, what I'm doing is, in fact, I could have, to be honest, I could have just put in an extra line over here in this table, Qn plus 1. You can do that. You can. That's why I'm putting those two tables, one on top of the other, so you can see that. But I wrote already something over here. You can put a Qn plus 1. Okay. Now, and then some of the other inputs. 1, 2, 3, 4. So I'm repeating this. It's coming in here. 0, 0, 0, 1, 1, 0, 1, 1. All right. Now, from a memory point of view, we want to know what is happening in the future, right? Or when memory is recalling, what is it trying to recall? Right? Okay. So 0, 0, according to our earlier table, 0xx, well, the moment clock is 0, we know it's memory. Right? If it's memory, it's trying to recall a previous state. So previous state in terms of Qn plus 1. Q of n plus 1 is future state. One step back is what? Qn. 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 Where does the word Q come from? Q is the Q and Q bar. Yeah, Q and Q bar, but of the previous state. But we don't have it defined. It's depending on what was there before, what was stored. Like for set and reset, we can say, yes, this is a 0. This Q will equal to 0. Q will equal to 1. You can be sure. But with 1, 1, right? I mean, with this particular case, we don't know. It was dependent on what was stored. All right, so it's Qn. Okay, now, what about this line here, guys? That line there? Our Q and Q bar is Q. Okay, so Q is current. Qn plus 1 is retrieving from memory. So there'll be Qn again, because that's memory. So instead of writing the word memory, we've actually given it a formula. So that's what we are trying to do over here. Why is it that we are moving from this table to this table? Why? Well, over here we've got some words, memory, memory. We want to put it in terms of an algebraic equation. We want to move to some mathematical Boolean algebra. So one way to do it is, if the current state is Qn, memory will recall Qn minus 1. Or another way to do it is, if the current state is Qn plus 1, memory will recall Qn, right? Go one step back. So either you're at Qn and you are recalling Qn minus 1, what happened one step ago, or you're at Qn plus 1 and you are going one step back, which is from Qn plus 1, one step back is Qn. So what we are doing is we are giving it a mathematical thing. Just writing an English word memory does not help us in our design process. We want some mathematics over here because we want to derive some formulas, right? So Qn plus 1, we're going one step back, so it'll describe Qn. All right, now, what is this line, guys? This one line, what will Q will equal to? Qn plus 1 will always be, it gives you a definitive answer. Always gives you a definite answer. So you refer to Q over here, eh? Not Q bar. Q bar was just to, the purpose of Q bar was more so to show us that, hey, the design parameter is being met. Right, now let's look at Q. Q will always be 0. Right? Okay, so this is what, okay, so over here, I can just put down, this is same as, dot, 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 same as Q. Same as Q from early on. But over here, Q was saying memory. Over here, see, this was memory. Memory. Okay? Now, what's the case over here? There'll be Q is 1. Again, Q. Now, what is the case here? We just say invalid. We're not going to even use it. There we go. So this is the truth table. The thing about sequential logic is that there's many truth tables. I'm showing you the derivation. Eventually you will come to a table called the excitation table, and we're heading that way. Okay, we're going to do many tables today. All right. Okay. All right, guys. So this was this table here is the truth table, which is basically an extension of this. Now we're going to rewrite the table. The problem with the original table, was that it was not giving us the original table. Well, we were using word like memory. It did not give a mathematical form for memory. So we want to now put it in terms of a mathematical form. Let's now go to the next step. The next step is the excitation table. The excitation table. Okay, the word is long. I mean the name sounds a bit freaky, but don't get too excited over it. Okay. All right, let's just put this here. Okay, now excitation table. So this here, guy, was the truth table. The SR flip-flop truth table. Okay. All right, guys. Now we move to maybe I show you an easier table, intermediate table beforehand. It's called the characteristic table. Okay, how do we get to the characteristic table? And I'm going to show you there's 4 flip-flops, right? There's 4 different types of flip-flops. If you can master this one, all the others will start to become really, really easy. Okay, so in the characteristic table, it's more like, remember what we say, Qn is the previous state, and Qn plus 1 is the current state, right? So Qn plus 1 is retrieving what the previous state is, right? Okay, Qn plus 1, current, Qn is previous, right? Or maybe another way to say it is Qn is current, then Qn plus 1 will become future. So what does the characteristic table do? Characteristic table, the main purpose of the characteristic table is that it, the main purpose of the characteristic table is that it, the main purpose of the characteristic table is that we're going to rewrite this table in terms of current memory and what's going to happen in the future. Or another way is just to say it is current and future, or current and previous. So let me show you. When I draw the table, you guys will start to visualize it. Okay, so if we have Qn, S, R, what is Qn plus 1? Remember, what was the main feature of sequential logic? Sequential logic has memory. So all we're talking about is memory. That's our target. Because otherwise everything is just combinational logic. Right? Okay, now 3 inputs. 3 inputs, obviously everything will be 8 possible combinations. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. 1 0 0 1 0 1 1 1 0 1 1 1. Is that everyone happy? Now I want you to have you got this on top there? So I'm just going to move my slide up. All right. Okay. Okay. Now okay. Okay, now I just want to let you know, just so that you don't get confused, Qn is the current Q, eh? Okay, Qn is the current Q, right? And Qn plus 1 is the future state. Now, in this table, what have we omitted from the table as compared to the previous table? Clock line is gone. The clock line is gone. Characteristic table is looking at the memory, how the memory plays a role, right? We've already dealt with how clock plays a role. Clock is very simple. If it's 0, the thing is in memory mode permanently. If it's 1, then you can play with the inputs. Right, now over here we're looking at from a memory point of view. Right? Okay. So if Q is 0, S is 0, R is 0. What can you tell me? What will Qn be? Sometimes they call this Qn, they call this Q star. Yeah, Qn plus 1, they call it Q star. But Q is the normal Q which you see now you've been looking at it from the time of the lectures. Okay, if Q is 0, right, let's put that thing aside. Let's now look at S and R. Let's just look at the table on top. If S is 0, R is 0, what happens? If S is 0, R is 0, from the table on top, what can we say? If S is 0, R is 0, it's in memory mode. And what does Qn plus 1, the truth table, what is Qn plus 1 equal to? It's equal to Qn. What is Qn? Qn is 0. So S is 0, R is 0. It's going to give you memory. Memory is based on what? Qn is equal to Qn plus 1 is equal to Qn. In this case, Qn is 0. So therefore, we go and write down 0. Right. Now, if S is 0, R is 1, according to our earlier thing, if S is 0, R is 1, what do we get? If S is 0, R is 1, we get reset, yeah, which is a 0. Reset, yeah, okay, and Qn does not play a role in it at all. Qn doesn't really matter, okay, because it's just fixed. 0, 1 will give you a 0. All right, let's now look at the next line, 1, 0. Let's look at line 3 now, line 2, 0, 1, 2. 0, 1, 0. Let's first look at these two. S is 1, R is 0. Therefore, what will happen? S is 1, R is 0. What are we going to get? Right? What are we going to get for Qn? S is 0, R, sorry. S is 0, R is 1. Sorry. S is 1, R is 0. We get a 1. Yeah, so we get a 1. Qn does not play a role there because there's no memory involved. Memory is only involved in the case of 1, 1. All right, let's look at this. If S is 1 and R is 1, if S is 1 and R is 1, hey, that's invalid state. We're not using that, yeah, for our flip-flop, not our latch. We have to refer to the flip-flop. Invalid. So until now we were using the English word invalid. Now we put a Boolean algebraic expression which is letter X. Invalid, not used, right? Just like when you guys were doing some of the tutorial problems, we had X, yeah. Okay, now like for example that BCD to 7-segment decoder, all those lines which were not used, we put X, 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 X. Okay, now let's now Qn is 1. If Qn is 1, let's look at S and R. 0, 0, 0, 0 in our earlier line was giving memory. Memory is what? Qn plus 1 is equal to Qn. So that's how 1. 0, 1. That's a straightforward answer. It's a fixed answer. 0, 1, we don't even, this 1 doesn't play a role now. 0, 1 will be what? 0, 1 will be reset. It will be 0. 1, 0 will be set. It will be 1. 1, 1. That's a no-go area. Memory does not play a role. So put it X. Everyone understood how we got here? Because there's one more table to go. We're going further. All right, this is the characteristic table. But they're all related. If you do the main table, the truth table, from the truth table, everything is just downhill. All right, okay. Okay, now, let's now move to the excitation table. I'm forgetting to put the name down, the SR flip-flop excitation table. Now, the excitation table is the other way around. Okay, what is the difference between the characteristic table and the excitation table? What is the difference between the two tables? Okay, the characteristic table, the memory is given, I mean the previous state is given, and we are trying to find the next state. Yeah? The target. What is the target? We are finding the next state. All right? Okay, this is once again, let me repeat this. The current state is given, Qn, and we want to find what the next state is. Yeah? Or the current state is given and we want to find, I mean, the previous state is given and we want to find the current state. We want to move one up. Yeah? So Qn is given and we're targeting Qn plus 1. What is happening in memory? Whether it's showing something or not. So sometimes it's giving solid answers, sometimes it's dependent on what is over here. Yeah? What is in Qn. Sometimes it doesn't need Qn because it's just a set or reset. Now excitation table is the other way around. Okay, so these two tables are opposites of each other. These two tables are opposites of each other. We put Qn and Qn plus 1 and we are trying to find out what our so in our excitation table, and they use both are in use. We're going to, in our design process, we're going to use both. In our excitation table, we say, hey, this is, it's from a designer. The excitation table